Well, hello, everybody. Yes, my name's Michael Priestnall from Cambridge Carbon Capture, and we're based in Cambridge, working with the university and also working to a lesser extent with Nottingham University and the Centre of Innovation at Cambridge Carbon, Centre of Innovation at CCS. So I'm just going to talk a little bit about mineralisation. Interestingly, they're not about putting CO2 underground and mineralising it, but actually doing this on the surface as a process. So I'm going to talk about...
Sarkozy, I think. How does he make? Yeah.
How one might do this. Whether one of the questions that's often asked about mineralisation is whether this is doable at scale. What we're doing in our approach to mineralisation and some very simplistic analysis of the economics behind it. My apologies for that simplicity. And wrap up with some pros and cons versus conventional geological storage. And with these comments we just had ring in my ears about communications. My apologies in advance if I'm trying to teach anyone to suck eggs and the level of the slides that I'm presenting, so I may well skip some as well. So I won't dwell on this. I mean, clearly this is carbon capture storage is critically important, and I'm not suggesting here that we don't absolutely need it. I'm really referring to the issue of, is there a business case for carbon capture and storage based on geological storage? And it's a very challenging issue for a number of reasons that we've heard about, and I won't say any more than that. And one of these technological alternatives that might be a route to addressing it from a business perspective, we believe, is mineralisation. And again, here in the Geological Society, my apologies for a slide of this type. But basically, what we're talking about is trying to do an industrial version of the natural part of the carbon cycle, the carbonate silicate cycle, where about 1 billion tonnes a year of CO2 are moved in this cycle between the atmosphere and carbonate rocks via weathering of silicate rocks, formation of carbonate ions and bicarbonate ions, and mineralisation of that to form limestones. Can we speed that up? And I won't say any more about that cycle. It's fairly obvious. So if we're going to do this industrially, I mean, essentially it's about taking carbon dioxide, reacting it with some source of calcium or magnesium or perhaps iron, there are alternatives too, and forming essentially limestone ultimately. That may be via producing bicarbonates as well in solution. It's dependent upon a number of process factors, not least pH. You need a high pH to do that carbonation. It depends obviously on the source materials that you're using as feedstock of calcium or magnesium, particularly particle size, temperature, humidity. Fortunately, it's an exothermic process, so it will happen under its own steam, but it happens very, very slowly. And that's the key challenge, that you need to put energy into this process, whether it be mechanical energy in making your particle size very small, or heat or pressure to make the process go faster. And again, very simplistically, but two generic approaches to mineralisation are to take carbon dioxide gas and react it in with solid phase feedstock materials to form carbonates. That's a company like Carbonate, that's a spin out from Greenwich University, is doing just that. The other day I went down to see a small process they have in operation in Kent, where they're using combustion ashes, which are high in calcium oxide, in combination with quarry fines, reacting that with CO2 to form aggregates. And it happens spontaneously and it happens quickly. but there aren't very many combustion ashes around, which is perhaps the issue of doing things at scale. The other generic approach is an aqueous phase type process where you extract calcium and magnesium from some source. You may dissolve the CO2 into an aqueous phase and react those together to form a precipitate of carbonates. Generally speaking, from the work that's been done to analyse these different processes, the aqueous phase processes seem to be favoured from an energetic perspective and a kinetic one. So is it feasible at a very large scale? And really, through much of the rest of my presentation, I'm looking at numbers at the global scale. So if clearly mineralisation can play, there's a business in there to be doing this in all sorts of specialist applications or small scale operations where there's money to be made, but is this something that can be used as a process to tackle the very large scale of emissions from coal-fired or fossil fuel power generation in general? And the short answer is we think it is. But just to look at some of those numbers, we've got about 7 billion tonnes a year or 8 billion tonnes a year, whatever, of CO2 coming out of fossil power generation. If we're going to mineralise that, we need something like 20 billion tonnes a year of silicate rock that contains magnesium or perhaps calcium to react with it to form output minerals and carbonates in particular. The kind of output of material, you might be getting close on 30 billion tonnes of mineral products. You've got to find some output, somewhere to put all of that material. Up to now, mineralisation as a process, the assumption has been that we're going to generate, if we were to use this kind of process, we would generate all of this material and we'd have to store it somewhere, maybe put it back into the holes in the ground that you've dug it out of. But one of the applications, if you get the process right, if you can produce materials that actually match what we're using already in the form of construction aggregates, then we've got a market already out there in construction aggregates industry worldwide that's about the same size as the amount of material that you'd be producing from mineralising all of our CO2, all of our fossil CO2. And the other question is there enough silicate rock around to feed in? Well, there's certainly enough magnesium in terms of its availability in the Earth's crust. Is that available in the form of minerals like serpentine? And I should just explain why a better mineral to use would be something like wollastonite, which is calcium silicate. There's more energy released in that process, and it's a downside easier to do mineralisation with it, but there isn't very much of it. So you need to have some source where there is plenty of material. The serpentine is very widely available globally. The Energy Technologies Institute has recently commissioned a study to look at availability of feedstock materials for mineralisation, and that work's being done by British Geological Survey and Nottingham University. So in our process then, what are we doing? I mean, the key first step is about finding our calcium or magnesium or any of those active elements. We're looking at a couple of processes that we think are very promising to integrate with our overall mineralisation process, which from the original title of the slide, we're using fuel cells in our process. Let me just explain a little bit about these two processes that I've mentioned up there. They're both closed cycle processes, which is important if you're going to have any kind of process on this scale. You don't want to generate any additional waste that one's got to deal with, or have huge quantities of other chemicals that feed into the process in order to do your mineralisation. So these processes both really just have inputs of mineral feedstock and CO2, and outputs of aggregate and a number of other byproduct chemicals that have value. So in the Alkali approach, one uses a high pH, highly alkaline solution to digest. I'm focusing just on serpentine for the purposes of talk today. digests serpentine, digests the silica in there, dissolves that up and leaves behind effectively magnesium hydroxide. That magnesium hydroxide can then be used to carbonate, form a solid carbonate precipitate from the alkaline solution once it's been used to pick up CO2. So if you're using something like potassium hydroxide as your digesting medium, potassium hydroxide will pick up CO2 and form potassium carbonate very readily. So you can have a closed cycle there that cycles between hydroxide and carbonate solution and regenerates that that hydroxide solution by precipitating solid carbonates. The second process, which is and Nottingham University is doing a lot of work on this process. This is a process that was looked at in the 1960s for digestion and extraction of useful, valuable materials from asbestos wastes. It involves an acid digestion this time, an acid digestion of serpentine. Obviously, you're taking the magnesium into solution rather than the silica phase, but it's faster and it's easier. And doing the acid digestion with something like ammonium bisulfate, gives us then a silica phase of amorphous silica. You can take out the amorphous silica, you can take out the iron that's in the solution as a separate product stream. You're left with a magnesium sulfate in solution, which then will react with a carbonated ammonium hydroxide, ammonium carbonate. It'll react with that to form magnesium carbonate, and the resulting ammonium sulfate can be heated to generate ammonia to feed back into the carbonation process, and ammonium bisulfate to feed back into the digestion process. So again, closed cycle processes. And for our purposes, in combination with the fuel cell, they offer us the alkalinity we need to operate the fuel cell, and they provide the magnesium or calcium salts to do our carbonation. So in terms of how do we do this with a fuel cell, I mentioned earlier that there's energy in the overall process available. So if we oxidize carbon to carbon dioxide, we get the order of 400 kilojoules per mole. There's a little bit more energy to be had if you can take that carbon all the way through to solid carbonate. So there's more energy there to be extracted. If you can do that process within a fuel cell, and what fuel cells are all about are converting chemical energy directly into electrical energy and bypassing as far as possible the generation of heat. That extra energy, or some of that extra energy, can be taken out as electricity, which can then be used to offset some of the rest of the energy that you need to for example, digest the mineral and grind the feedstock material small enough to execute the CCS process. So that's where energy is coming from, and why using a fuel cell approach is a low energy route to doing this. And of course, one other thing worth mentioning about fuel cells that it seems strange to me that the CCS industry hasn't taken this up, or for that matter the fuel cell industry, that even in geological approaches to carbon capture and storage, it's the capture of carbon dioxide that is the most energetically costly part of the process. If you use fuel cells to convert fuel to electricity, and you're putting a hydrocarbon fuel into a fuel cell, you automatically generate pure CO2. So you've already paid for the formation of the generation of pure CO2 streams. So fuel cells are extremely relevant technology for CCS. And we're doing something slightly additional to that here, in that we're taking that CO2 out, as I say, as a solid. So just to explain how that process sort of works in the cycle, if it's say for an alkali fuel cell which would have potassium hydroxide in there as an electrolyte, that potassium hydroxide will pick up any CO2 that's in the system, and that's including the CO2 that might be in the air that is going through the fuel cell. So it picks it up extremely rapidly, and of course potassium hydroxide is being used, and potassium carbonate are being used as carbon capture solvents effectively in conventional CCS processes. So it picks it up very, very readily. But of course that consumes the hydroxide in generating a carbonate. We effectively then take that carbonate and precipitate out the dissolved, the carbonate ion that's in solution and turn it into a magnesium carbonate or calcium carbonate solid, and regenerate the electrolyte to go back into the fuel cell. So again, it's a cyclical process. And one of the things that we've worked out how to do is this process could work starting with fuel as the input to the system, but perhaps more relevant from a business perspective, we don't have to run a power station using a fuel cell. We can actually use CO2 from a flue gas as a feedstock into the fuel cell and generate power from that small amount of energy that is there from turning CO2 into carbonate. So we can work with flue gas and point sources of CO2. Forgive me, I'll just skip that slide in the interest of time, but really that was just an illustration of what this might be like on a 500 megawatt power station scale. But to skip to the very simplistic analysis of why it might be profitable, we've got essentially revenues being generated from the materials that come out of the process. So we're going it is, excuse me, just worth dropping back to that earlier slide, because the outputs from the process are primarily aggregates, but there are also some additional high value materials in the form of the metals that were in the feedstock material that you put in the first place. So that suggests, okay, let's look for feedstock silicates that actually have some additional metals in, and serpentine would have iron and nickel and cobalt in there in some quantity, which can be extracted as value. But maybe other mining processes where the gangue contains metals that are otherwise not worth extracting, there may be more value. Someone in an earlier question, I think, mentioned rare earth metals and whether there are enough of those to support the renewables industry. Leeds University is working on digestion of low-grade titanium ores to produce titanium, but the driver for using those low-grade titanium ores is the fact that there are metals like niobium in there to be pulled out as well. And by the way, it also captures CO2 in that process. So those are the kinds of things that need to be brought together to make an interesting business case. And on that sort of interesting business case, I mentioned carbonate earlier. The driver there is the fact that some of the materials that can be fed into the process may be hazardous waste, and there's value to be had from those. So we're making revenues, or potentially one could make revenues from the products that are produced. Adding that to the value of CO2 abatement, and here I've just used the sort of current levels of value for CO2 on the ETS. The £50 a tonne that I put in for our mineralisation cost here, that I believe is sort of a worst case scenario. We've done some initial looking at the energy involved in the process of mineralisation. Other people are doing an awful lot more work on this. But as one integrates these processes, and as new processes are being developed for mineralisation that are much lower energy, that cost of executing the mineralisation process is coming right down. So I think those numbers are going to fall massively. And so in a worst case scenario, even at £50 a tonne, it's possible to make money out of doing carbon capture and storage. Drivers as to why this might happen now. What can we do this sooner rather than later? Well, there aren't many drivers. One of the key ones that's out there at the moment is that you can treat some, if instead of taking serpentine as a feedstock, you take hazardous waste as a feedstock. By carbonating them, you turn what was a leachable metal into a stabilised metal and reduce the cost of dealing with that waste. And that reduction in cost can be as much as £100 a tonne. And that can make for a very compelling business case. And that is already out there and happening. in the context of the various competitions, obviously there's a major UK competition on CCS projects at the moment, which are all focused exclusively on geological storage and the kind of processes we've heard about so far. There is an expectation that those bidders have got to say how this is going to be, stand on its own 2 feet post the demonstration phase. And that is a very, very difficult question to answer. The assumption is that carbon prices will rise and the learning curve of doing these projects will bring the cost down so that it'll somehow cross over. But mineralisation in there as an option is one route to making that economic case, and we're starting to have some of those conversations. I've already talked about some of the value of metals and other things that one can take out of it. Interestingly, we've been talking to folks in the construction sector about low carbon building materials. If the major output of this process are aggregates, cements, concretes, that you can get cements out of this process, a small proportion of cementitious material that are low carbon. Is there some great value in those low carbon materials? Well, actually today there isn't. There is no financial mechanism to get any benefit from that. That may come, but it's not a driver at the moment. And of course, if one can do these processes on a mine in the right country, maybe one can get value today from clean development mechanism. Wrapping up with the last couple of slides. We've got some clear differences over conventional geological storage as a process. I mean, we can generate money from it. We don't have this requirement for infrastructure to be in place in the form of pipelines and sort of proven and established depleted reservoirs to fill. And a conversation with Statoil some time ago, I understood from them it takes about 6 years to take one depleted site and sort of qualify it to accept CO2. We've heard about issues of supercritical storage of CO2 and public acceptability. Generating a solid building material is rather more attractive from that perspective. And interestingly, I think this kind of process, because it has relevancy for treatment of wastes or for an alternative process for minerals extraction or metals from mining processes, there are other markets to take this kind of process into at a smaller scale as one builds up towards a real CCS marketplace. So it allows one to get going with the process straight away. And a few other points too. But there is this key logistical issue that we've got huge amounts of material flowing through the process in order to do our carbon capture and storage. So that's going to require some pretty significant changes. I mean, at a very high level, one of those changes is that instead of the aggregates industry mining 25 billion tonnes a year of aggregates and crushing stones for all of the applications that aggregates are used for, instead they need to switch to mining serpentine and crushing that and feeding it via power stations to produce the carbonate aggregates that then go back into those same broad uses. And in terms of operating a power station, if everything were to happen on site, you might need somewhere between 3 and 10 times the amount of material flowing in as you would currently in the form of coal. It is possible to split the process so that you do your magnesium and calcium extraction at the mineral site and just move the magnesium and calcium around, and that may be a much more sensible approach to do it. So it is compatible with global scale emissions. People here will know an awful lot more than I do about the availability of serpentine, but my understanding is that there's more than enough of that. There's markets to take the material. It is a profitable process if it's got right. There's still, of course, a huge amount of research and development and crucially demonstration to be done here. we have a particular technology that is aimed at bringing the process down in the form of you know, the energy and the cost into the process. Others have got some very good processes too. But it really does need to, we do need to get this kind of approach, mineralisation, out there and operating and getting some learning experience. It was a bit worrying for me to go and see this process in operation that Carbonate are doing, which was great to see it happening, but they reckon that was the world's second largest project in carbon capture and storage as minerals, and you know it was a tiny little operation. I do have a photo, I'm sorry I didn't include it. So lastly, I just wanted to mention the organisations that we've been working with and thank them for their financial support and their technical support. Thank you.
Okay, time for a couple of questions. Please, in the middle there, and Stuart next.
Yeah, I have a question on several things. First, okay, the most important, that slides to show the rough calculation of revenue and cost. Over how many years was that based on?
Yeah.
Was it present value calculation, and what's the capital cost for that?
So back of the envelope calculation, but done on figures that obviously we've gone out to look for. This is based on what our CO2 emissions, global CO2 emissions from from coal-fired power stations. So if the process were to be applied today at a global scale, would it make financial sense to do it? I mean, we've also done obviously the calculations on a single power station to do it at much smaller scale. But I'm trying to present, does this make sense to do as a large scale? In terms of the detailed analysis, we've done some work with Judge Business School that, and we put the question to them, really, we've got this process, how does it compare with conventional coal and with conventional CCS applied to coal-fired power stations? Is it a financially sensible thing to do? Is it a crazy thing to do? And the broad answer from that was, and the inputs to that were I've worked in the fuel cell industry for a number of years, so a reasonable idea of what fuel cell system costs are and what can be achieved. So to put in some numbers for CapEx for the kind of system, but very high level numbers, and expectations from our understanding of what people have done on mineralisation, analysing the energy involved in terms of operating costs. And the broad answer that came out of that was if we can get if we can get a net around about a net £10 per tonne for materials flowing through this process, it will be extremely profitable.
Okay, one more, Stuart.
Yes, I was just wondering, first of all, where do you find serpentine around the world? And have you factored in the costs of mining it and transporting it to your point sources of CO2?
Well, I mean, the answer to that first question is hopefully being addressed very thoroughly by the Energy Technologies Institute, which has launched a major study into the feedstock materials for mineralisation, as well as the kind of processes that can be used. And Giorgio commented earlier is involved in that, I think. So I don't know the answer to that question, but my understanding is that there'll be someone here who can answer the question, that serpentine is the most widely available of the kinds of feedstocks. It's not necessarily the easiest material to use because using magnesium's trapped in the silicate cage. It's very difficult to get it out. So the analysis here is based on the absolute hardest thing to work with, and it should work with serpentine. And the other question.
The other question was, what have you factored the costs of mining it and transporting it?
Well, I mean, broadly, yes. In our work with Judge Business School, that was factored in there, but at a very high level. There's what are the prices of aggregates today dug out of the ground as moved around in these sort of 25 billion tonnes around the world? What would be the difference in taking materials out to put into our kind of process? And aggregates are around about 3 to 5 pounds a tonne. There's an aggregates tax that's out there at the moment of £2 a tonne for digging it out of the ground. Those kinds of things sort of wrap into that calculation as well. And transport is a factor, yes.
Okay. All right. Thank you very much, Mike.
Thank you.